All right, well, it's 8:50. Let's get started. Welcome back. It's good to see everyone this morning, or as many of you as I can see. And I do think it's useful to sort of start each day off with just a really quick look at the schedule. We don't have to belabor the point too much, but here we are on Friday of the first week. And what you would notice for today would be the first homework should be available for you to see on Canvas. So you can click on that starting now. Of course, wait until this wonderful lecture is over, and then you can click on that. And it's a pretty straightforward assignment. So one thing I did add because a couple people did ask is to make sure that we have in that assignment a pretty clear description of certainly it's based on what we've been covering in class, so that's all fair game. But what section of the textbook roughly corresponds to where those questions are from? And so this homework is a little bit of just chapter one stuff, the really high level stuff. That's all we've done so far this semester, as well as a very small amount of what I would call CPRE 281 refresher questions, which maybe something that will just take you 2 minutes, or you may have to go back and think about some things. And like with anybody else, anything else, certainly let me know if you are having questions. Are we having some internet challenges this morning, or are things okay in terms of video quality and all that? Looks good on my end, which isn't very helpful. Okay. Okay, that's excellent. If it was 480p, that's probably still okay. I am not doing any screen sharing right now. This is all just my camera feed with the screen in the background. So it could just be a function of upload speed this morning, or internet speed on campus, or various other things. The truth is also that not an obvious fix for that either if things are not going all that well. So that's a good thought, though. Although today does involve reading what I have kind of on my screen that to a little bit more extent than other days would. Just keep chatting and let me know if you're seeing that, hey, I wrote something down and you can't read it all. I don't want to waste your time either. So uh, let's monitor that and stay on top of that. I'll monitor the chat window as well. Hopefully the audio is coming in as well. You can still hear my silky smooth voice, and that's important as well. Okay. It's better than nothing, I guess. Yes, thank you, David. Um, Okay, so that's all I wanted to say about the homework. So it is assigned today. It's assigned on those Fridays. It is due before next Friday's class. All submitted on Canvas. I always call them the low stakes, a low stakes assessment, and that's everyone should be able to do all those for the TAs, and you can even see the grading rubric that they'd be using here. It should be pretty straightforward. Click, 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 click. Okay, you understood the questions. Moving on. To the next one. There's a lot of students in this class. Um, a lot of homeworks that have to be graded, and not a lot of time to be able to do so. And the other thing I wanted to mention is, we did have that quiz on Wednesday, and everyone did great. I looked at all 143 submissions. I had mentioned before that for those quiz questions, there's sort of a question for you as well as a question for me for a lot of those quiz configurations. And the question for me in this first week was just that generic question of, what's your interest, or alternately, what's your background in computer architecture? What brings you to this course? And there was several interesting categories of answers. Quite a few of you said, well, I'm a computer engineer. I'm required to be in this course, so here I am, and that's a perfectly valid answer. And that's my job this semester to engage you in the class and help you learn a lot this semester. That's a great answer. Um, Others said, I became interested in computer architecture because this is about a dozen people who said, there's a YouTuber who makes a lot of videos about building your own computer from scratch. Ben Eater is the guy's name. And that led me down a rabbit hole of just, I viewed about a dozen of his videos, and they're really cool. You can check those out. That's, using discrete components and breadboards, and building an 8-bit microcontroller from those. I would think that if you watched those videos and got the big picture of what he's doing, he's operating on a slightly lower level of abstraction than we will in this class, because he's worrying about physical routing of wires to get things to fit on a breadboard, and we let the tools take care of all that for us. but conceptually, if you watch those and you generally understood or appreciated a lot of what's happening in there, um, you'll be fine this semester. I mean, there's a lot more detail. We're doing a lot more complicated of a processor than what he was building in that series of videos I was watching this week. But it's pretty cool stuff. And certainly, I'm dating myself, but when I took microcontrollers course as an undergraduate, which for us, where I was separate from an architecture course, that's how we did it. So it was discrete components and breadboards. Um, Fun when things work, but horribly painful when things don't work. And trying to trace down why is this not working? It turns out your wire is off by one little position, and there's no tool to tell you that it's wrong. You have to just trace things down on a bit by bit level there, and that's actually pretty painful, and it limits how much complexity you can deal with in your design. But I thought that was kind of cool. That was something that he's obviously popular enough that enough of you watched his stuff, and I thought it was pretty cool. It was cool stuff. I heard also from a few the cybersecurity engineering students who said, "Well, I just have to take this course. I don't really see why." And for you specifically, that group of students, and it was definitely a handful. I disagree. I'll just say that, and maybe we need to do a better job of motivating this course for computer security experts. Understanding architecture is vital for a pretty wide class of cybersecurity expertise that you would then go on to develop. A big chunk of understanding security and systems is at the ISA level and below. And that's actually always been the case, but it's even more prevalent now than it was just a handful of years ago. So um, we don't do hardly any of that intersection between computer architecture and security in this class. This is just a class for everyone to learn the basics. That's something that hopefully you'll get a chance to learn a lot about with the fundamentals that you would learn in this particular class. So anyway, so that's my takeaway from our first quiz, and everyone did great. So today's Friday. Today's our so-called Friday fun, and fun is relative, but I find this stuff fun. I wanted to provide just sort of my high-level overview of the language that you will be spending so much of your semester wrangling with, and that is VHDL. So as I mentioned, if we are having resolution issues today, this is where it's going to really come out first. So we will give this a try, and if it's not legible, um, I will probably just shut things down and do this offline, and that's fine as well. So this class, beyond being a computer architecture class, is very much a VHDL class. One second here. Oh, that's lovely. Okay, this is a VHDL class. Who's the first person in the chat who can tell me what VHDL stands for? You've all had to Google it, so no one knows, and that's okay. And I appreciate the first person to jump out there and make a suggestion, a very reasonable suggestion, a very good suggestion, and an incorrect suggestion. So I appreciate that. Yes, very hard obscured language is a good one as well. It actually is one of those weird recursive acronyms, which was all the rage in the 1980s. It stands for, and it's going to take me a while to get a little used to how I'm writing on this here. Very high speed. We'll talk about that in a second. That's actually the V. So VHSIC. I'm going to mute you here in a second, whoever's got your mic on, and that's okay. If you have a question, chat's probably better, uh, unless there's something very pressing like, my fly's down or something. Please let me know that immediately. So it actually stands for VHSIC, Hardware Description Language, where VHSIC stands for Very High Speed Integrated Circuit. There was a time, and it sounds kind of silly now, where that distinction between um, high speed, low speed, and then very high speed was a relevant distinction. Likewise, you've heard probably the term VLSI, very large scale integration. There was a time when that was an important distinction, and it's really not anymore. I mean, large and high is in very relative terms, and it doesn't really mean anything. So, but that is what it stands for. I think commonly people think of Verilog versus VHDL, and having just perhaps taken 281, where you did a little bit of dabbling with Verilog. Now in this class where it's all VHDL, um, they are conceptually, in terms of the design of their language, roughly one-to-one equivalents. The syntax is just different. Um, Oftentimes, I think for someone, it's whichever one they really learn the best first is the one they prefer to use. But in almost all real world designs that I work with, we use a combination of both, and you do the same exact things in both. And that's one of the things I'll want to have a takeaway from today, which is syntax is just syntax, and we will learn the syntax pretty quickly. Where to put the commas and semicolons, how to assign signals and port maps and things like that. Just in having completed a big chunk of lab number one, you already know a lot of that, and there isn't that much more to it than what you've done in lab number one. But what is important, and um, what is new to, I think, all of you, is the fact that it's the design philosophy is fundamentally different. And I don't really think 281 covers that at all. It's, let's accomplish this task. But once you start to want to design more complex things, and in 381, and certainly in some of the follow-on courses as well, there is a design philosophy one needs to follow. And if you don't follow that, there's no syntax in the world that's gonna help you. So it doesn't matter if you choose Verilog or VHDL. Both provide you uh, enough things to get the job done, and both provide enough features for you to shoot yourself in the foot with a design. And my goal in this class is that as we go to more complicated designs, you never feel that you have to start over this semester. In 488, when I used to teach that, we only had one module that used VHDL. It was a bit more advanced than what we would do in this class, and if we weren't careful, people would have to completely start over, and that's a pretty frustrating and painful thing. Maybe everyone has to experience it once in life for these suggestions to really take hold, but my hope is you don't have to do it this semester. That can happen to you at some other point in life, perhaps. So this is all me today. This is all just my opinion, I guess. And so I have my major commandments for VHDL, and that's what I'd like to cover. And now that I write that out, that sounds a little conceited that I have commandments. Okay, so it's my four uh, rules of VHDL. Even that, that implies I know more than the language experts themselves. But let's say my four strong suggestions for VHDL that if you follow these ways of thinking about VHDL, and these are hard earned suggestions over a period of decades now in terms of how to think about hardware design, and where the language itself can either help you or get in your way. If you internalize these, I think you'll find this semester to be a less frustrating experience, and you may find you really enjoy it. And I really enjoy it, and it's something that people can really become very good at and become very productive in. And again, it's actually one of the things I like about this course, right? If I were teaching a C programming course, which I also love, half the class would already know a ton, and half the class would know very little. And some people think they know a lot and know very little, but at least for the most part for VHDL, in a class of 150, maybe we have one or two students in that class who already have a lot of VHDL experience. So it's if you feel confused and feel like it was all Greek to you in lab number one, that that's kind of the point, and that's everybody this semester. So don't feel that you are at some disadvantage if it seems so different to you and so foreign to you. That's sort of by design, and that's how everyone should be feeling. So we'll start with my first strong suggestion, and these aren't necessarily in order, but they're all pretty important. And the first one has to do with the actual definition itself. So whether it's Verilog or whether it's VHDL with this somewhat meaningless recursive acronym here, I would say the most important word in this acronym, in the name of the actual language itself, isn't language. I mean, hardware, I guess, is important, but the most important word here is description. And I'm going to talk about what I mean by that, where with regards to description, um, I think it's important to talk about how you're describing something and you're not actually programming something. So that would be my first commandment or first strong suggestion, that hardware description is not the same thing as programming. And we'll slip into using somewhat imprecise terminology, and you'll catch me doing it if you pay close enough attention, where I'll say, when you're programming your VHDL, do this, and that's okay. It's not like I'm trying to police language here, but philosophically, conceptually, those are two fundamentally different things we are doing. When we're working with VHDL or with Verilog, we are not programming. We're not programming in any sense of the word. We are describing hardware. Yes, in both cases, we're editing a text file that has lines of code in it, um, but fundamentally, it is different when we are describing hardware. And part of that has to do with what the languages themselves provide for you as feature. If I were to draw a really mediocre Venn diagram here of the big oval would be what VHDL as a language allows you to do syntactically. I will call that VHDL for VHDL language, or VHDL for specification. What you are able to legally specify in the language VHDL. That is all a VHDL will say as a language. The whole universe of code that you could write for VHDL that would compile and would likely simulate properly in Model Sim. There is a fairly strict subset of that is actually relevant for hardware description. And for people who are relatively new to the language, and sometimes for those who have years of experience, that can be a little bit of a frustrating thing, to be honest. So it is a strict subset. We'll call that VHDL. For description is probably a little ambiguous, but VHDL for hardware synthesis. A strict subset of the entire language, of the stuff that will compile, is actually all that is meant for stuff to describe hardware. And so you will potentially find, if you go off to Google and try to find solutions for things, whatever, but if you just try to reason from base principles of what you can find as valid syntax, that you will be writing programs in VHDL, and you will not be describing hardware in VHDL. And that will work up until about week 7 of the semester, and that will completely stop working, and you may have to start over. We have to be very conscious, unfortunately, from day one when working with VHDL, that we are trying to describe hardware, and what we are writing in our VHDL should correspond to a specific piece of hardware we're describing, and not ever corresponding to a sequential program that we're trying to write in the C, C++, Java meaning of the term sequential programming language. Because, not to belabor the point too much, VHDL does let you write sequential programs as well. You can use your for loops and while loops, and in some very specific circumstances, that is also still acceptable for synthesis. But by and large, once you find yourself reasoning about a .vhd file that you're working on and thinking about, I'm going to do this, and then it's going to do this, and then it's going to do this, you're actually programming, and you are not describing hardware anymore. And you may get it to work for that week's lab. ModelSim may spit out a result, because ModelSim will simulate all of it, that is correct, gives you the right output. But when it comes time to map it to hardware, and that's what I'm using the term synthesis in this context for, when it comes time to load it into Quartus or Vivado or Lattice or any of those tools are going to give up pretty quickly. And there's not going to be a quick workaround then. If you've been spending your time writing programs in VHDL and it all works perfectly in simulation, you're not half done. You're closer to 0% done than you are half done if you were using that broader world of VHDL that is not hardware amenable. So you may find me becoming a bit strict about that, when you're on Discord or something and you suggest, well, here's my code, I need some help with it. You may hear me say, good effort, but you got to kind of rethink this, and you can't this isn't fixable. This has to kind of start over and be done um, the right way, and that's to save you more pain later on in the semester. So that's a pretty important thing to start with. Um, yes, we can use the term VHDL program. It's fine. I'm not going to police the actual language we are using, but at the same time, your mental model should be that we are describing hardware and that we are not writing actual programs here. I see a good question in the chat. We're going to get to that in just a minute here, and we can mention that a corollary of this is that there's three different styles of VHDL description or VHDL programs that we have here. Um, we'll put that, styles is what the free range VHDL book refers to it as. It's a perfectly fine word. Three different ways of developing your code in VHDL. One second. Okay. And you've already seen maybe some of these keywords when just looking at the lab number one. The first one is structural. So structural VHDL is a description of structure, right? So when we're doing our structural VHDL, the point of it is thinking about our design and our hardware that we're describing in terms of the underlying physical structure of it. And in this context, that means what are the actual components and their mappings. We will talk about ordering of lines of statements in VHDL in this context in just a moment here. Um, when you're describing things structurally in VHDL, you're generally your safest. Here, I'll turn my face off here. You're generally your safest when you're describing things structurally. You should think of it as sort of like either Legos or Tinker Toys. If the parts fit into each other, whatever you build is going to be valid from a hardware perspective. There's still pitfalls along the way, but certainly as we're just describing our structure here, um, we are really just worried about what components in our system and uh, primarily what are the ports associated with them, what directions are the ports going in. So if we have a little component here with a little output port as well as potentially an input port, and with our structural VHDL, what we're really worrying about are those port maps that you've seen already in lab number one. What are those components? What are their ports? And then what wires do we use to connect those ports together? And this is a pretty common abstraction where you have one component that has an output port and it's going to connect to the input port of the other component and vice versa. That's supposed to be a wire. That's fine. There's still potential issues here if you're not careful, right? If this output port happens to be an 8-bit value and this input port happens to be a 16-bit value, well, your structural VHDL is still going to throw, depending on the compiler and runtime environment, it's going to throw either a compiler error or warning or a simulation error. Those can be kind of painful simulation errors as well. But in our structural VHDL, we are just really thinking about what are the components I need in my system and how am I going to wire them together. The main thing you're designing is, your block diagram, as well as you're going to want to call, and label the wires something appropriate. This is going to come up a lot in lab number 2 next week, where we're doing a lot of um, structural layout of 281 style components we're doing in lab number 2. As long as you can think in these terms, you're going to be pretty safe here in terms of code that's going to compile, and you're well outside the concern of writing VHDL that's not going to correspond to any hardware at the end of the day, because you're just mapping existing blocks together. There is a little bit of a, turtles all the way down, right? People will say that structural VHDL is safer, but your design can never be entirely structural VHDL. These are our black boxes. We've wired them together. Ultimately, there's got to be something going on inside one of those boxes. So it could be structure and structure underneath the structure and structure underneath that structure. That's all good. And I can show some designs maybe next week showing what a really advanced design looks like in terms of that resulting structure. But ultimately, there's got to be a component that actually does something. So structural VHDL is great to use. It's very common that your topmost level component in your design is just entirely structural VHDL. But ultimately, your lowest level components have to be doing um, some actual work, right? Some arithmetic, some logic, something actually has to be done here. But having drawn out that picture, before I forget, that does actually lead us to the second, I'll call them strong suggestions. This one's closer to a commandment, but that's fine. This is pretty important to the extent that I even wanted to make a separate video just on this. And if I find the time, I'll do so before lab number 2. It's probably most important in lab number 2 in terms of alleviating frustration. But this is about a implementation philosophy for when working with hardware design, and that's draw first. Draw your schematics first, whether it's pencil and paper, or whether it's back on the napkin, whether it's in Draw.io or Visio, whether it's beautiful or ugly. Draw what you're wanting to describe first. Always. The lab assignment requires you to do it, but people don't always listen. Well, it says I should draw the schematic first, but I'd really like to be productive in lab, so I'm going to open up my text editor and start, developing in my VHDL. I really never want you to do that. Maybe by the end of the semester, you'll feel comfortable enough with VHDL that you actually have drawn first, but it's just entirely in your head, and that's fine. But you're still drawing first. It's just a mental model that you've gotten enough expertise that you don't have to put it on paper yet. But you should always be drawing first and then coding second. To the extent I've asked the TAs that later on the semester, when you're stuck with not U drive problems or other problems, but actual design implementation problems, the first question they should be asking you, and they should be somewhat insistent on this. So if you find your TA has been very insistent, because I've asked them to be, should be, can you bring up your diagram? And you're designing in VHDL, ideally in a 2-monitor setup. But if you don't have it, you don't have it. That's fine. Should be one monitor with your diagram, your schematic, and the other monitor where you have your VHDL or model sim or your simulation open. It's going to help you adhere to that first rule much more easily as well. As soon as you've drawn this, you're not going to have any problem. You've drawn what components do I need? What ports are they going to require? Even to the extent of, is that an 8-bit port? Is it a 16-bit port? As soon as you've been able to reason about all that and actually drawn it out, and as well as soon as you've actually provided some names to the actual wires that are going to be necessary in your design that are going to correspond to the signals in your VHDL, your syntax is going to be extremely straightforward. It's going to be very hard to implement this design wrong once you've had it drawn out. And similarly, this issue of a structural error where you have an 8-bit output port and a 16-bit input port, you're going to catch that before you write your first line of VHDL, right? That actual wire, as you draw it, you're going to say, well, something's not right here. Well, how did this happen? Do I have to concatenate zeros? Do I have to do something to make it fit um, with the rest of the system? It's going to be a necessity. We don't grade the diagrams based on how beautiful they are, but on how comprehensive they are. And it's so important to me that that's the first question I want the TAs to ask you when you're stuck on I can't get the adder to give me the right result. When it's a implementation issue, it's always let's bring it back to the diagram, and let's walk through both things at the same time. Oftentimes, once you've done that, you will find your problems very quickly, independent of the style of VHDL that you are following. So be prepared for that. This is true for structural VHDL, where it's most obvious that drawing it out helps, and it's true for the other styles of VHDL, potentially even more. Okay, so that's the second rule. That's a fairly critical one as well. So there are the other styles of VHDL. Let me bring this up here a bit for me. Other styles of VHDL. Second one would be data flow. And in data flow VHDL, what you are doing is describing functionality via what's referred to as concurrent signal assignment. So I ran a little bit of out of space here, but that's what it refers to. So if you hear the term concurrent signal assignments, that's referring to data flow VHDL. That's supposed to say assignments. Take my word for it. With our concurrent signal assignments, the idea is that we're describing data flowing through a circuit, and we're using the built-in VHDL data flow operators to then infer logic from the data flowing through a circuit. This is something that a couple people already asked about that in the chat here. This is something that can trip you up at first glance, but generally, when working with, I mentioned this for structural VHDL, the errors are usually pretty quick to spot. With data flow VHDL, it's hard to screw up this issue with regards to writing unsynthesizable code. Generally, anything you put into a data flow statement in VHDL, because of its simplicity, will correspond to resulting underlying hardware. But they are concurrent signal assignments, and that's something that can kind of break your brain a little bit until you get used to it. So the data flow signal assignment operator is that you can call it less than or equal if you want to. That's meant to be like an arrow pointing towards that output. That's what they're going for with that syntactical feature there. That here's a wire getting a value that's getting assigned, and you're always going to be using other signals as well as some of the sort of built-in operators in VHDL, of which there's just about a dozen. There's really not all that many. That's what that free range VHDL guide is doing for you. It is saying we have um, this set of operators. Here's the hardware that they correspond to, and for our purposes, what's nice about this is all that we have to do in this class can be broken down into 281 style logic gates. And that's a pretty common design philosophy. Use data flow elements as much as possible when your hardware can be described via data flow elements. And you can infer muxes and you can infer whole adders and things like that via just data flow operators. There's a decent set of them that you can use. The tools are all designed to understand and to support those and to infer hardware from those. And then when you need more complex functionality, you think of the structure of the system and you wire up your structural VHDL accordingly. So if we were to have that C statement, or C is equal to A and B, that in your mental model, in your diagram, and the question does become, to what extent do I have to draw out individual gates in my diagram? Well, in week 2 you do, but later in the semester it becomes less of an important thing. If we make that A, I don't know why I drew it as that input, and make that one B. That data flow statement is describing that gate, and that's the terminology that's going to be clearest for us as we go through this semester. We are describing that gate via that data flow statement. Where this can, I mean, and that should be a pretty straightforward thing in terms of and XOR, the basic Boolean logic all kind of works. Your VHDL text editor will do some nice syntactical highlighting so you know if you've spelled things correctly and things like that. Um, I heard something incorrect in one of our office hours earlier this week. So VHDL is not case sensitive, which can be very annoying. I mean, I guess it's six of one, half dozen of the other. So if you already have a signal called uppercase C, you can't have a second one called lowercase c. So you have to be a little bit careful here. We'll talk a little bit about where those operators are defined under. There's a little bit of complexity associated with that, but yes, you could do an AND gate for entire buses as well. Where this gets a little bit trippy though is because they're concurrent signal assignments in my VHDL. If that was line 73, on line 274, I can write this. I don't recommend writing it, 200 lines apart, but it's certainly valid. Where A is actually equal to D or E, and that would be describing hardware. Oh, look at that. Describing hardware that has an input corresponding to A that is actually the result of an OR gate And we would still want to label that A in our diagram. I just had to kind of move it over there, where that is D or E. If we were in our programming mindset as opposed to our hardware description mindset, this seems wrong, I think, to many of us, right? Well, I've declared this variable named C that reads from A and B and then does an AND. But then I only actually write to the value of A later on in my program. And I understand thinking about it that way. But that's not what we're doing when we're describing hardware. The word variable exists in VHDL. We're going to pretty much avoid it all semester. The concept of a variable does exist in VHDL, but for us, we're working with concurrent signals. So the better way to uh, refer to, let me be a little bit careful here, but the better way to refer to what is happening here is that we have signals C and A, and we are assigning C to infer an AND gate, and we're assigning A to infer an OR gate in our design. So the actual order of these two statements, because they're all happening concurrently, right? Hardware doesn't do this operator, then this operator, then this operator. That's our sequential programming model. That's our interpretation of C code. That's our instruction fetch, decode, that's a byproduct of instruction fetch, decode, execute. There's no instructions happening here. This is us describing that hardware. It's all happening at the same time. So there's no issue if I put these two statements in any order in my data flow VHDL. The resulting description of the hardware is exactly the same. So those are referring to concurrent signal assignments. And that's what data flow is. It can still be extremely useful. And in fact, if you hear someone talking about, well, structural is much better to use than data flow, or you should avoid behavioral VHDL at all costs, that's a sign they have, that dangerous level of knowledge of VHDL and not necessarily, that mature level of knowledge. It's not really a case of one being better than the other in any way, shape, or form. The philosophy I'm pretty sure you should be following should be, what is the hardware I need to describe? What does my diagram say that I need? And what syntactical features does the language provide me to be able to describe that hardware? This same exact OR gate connecting to an AND gate could have been done via some structural mapping, right? We could have had a component called AND gate and a component called OR gate, and we could have done some structural VHDL where we do all the port mapping of that to connect those two things together. At some point, it's just a matter of, personal opinion, which is a better way to do things. In my opinion, this would be my design philosophy. If you can describe what you're doing in Dataflow VHDL, that is the most programmer efficient way of doing it in terms of lines of code. This is literally lines of code, 2 lines of code. The structural equivalent is going to be like 25 lines of code to define the components, declare the intermediate signals, do the port maps. It's kind of wordy. Maybe you've already seen that, in lab number 1. And it's equally safe. It's not less safe than doing things entirely structurally. The most important thing is this, right? Once you have this and know that this is what you want to do, or conversely, this is what you want to do, the syntax, may give you a couple different ways to do it, but they're all going to be perfectly fine ways of doing it. And then finally, we have the third flavor of VHDL or style of VHDL is so-called behavioral. And again, I wouldn't trust someone who says you should never use behavioral VHDL. People use it, ubiquitously in all complicated designs. But I think it would be a fair thing to say that if we are worried about this region here, where your design works in model sim but fails entirely when mapped to an FPGA board, this danger zone here, that is all behavioral VHDL that does that. It's very hard, and in fact, I don't believe it's possible to write a data flow VHDL that will not synthesize or will not be valid from a synthesis perspective. But it is the behavior where it gives you some features. Behavioral VHDL you can read from a file, right? You can open up a file, read a string of text from a file, and store that as a signal. That's a very useful feature from a programming language perspective. It's an extremely useful feature. doesn't correspond to anything in hardware. You're definitely no longer describing hardware once you're doing that, right? What does it mean to have a piece of hardware that's reading from a file? Is it going to infer a disk drive controller and an operating system? No, it's just it's there to help the programmer out. But in general, your behavioral VHDL allows you to do sequential statements, which can be extremely useful for describing sequential operation of hardware. We're going to limit a lot of our usage of behavioral VHDL such that it basically is an equivalent of what you could have done in data flow VHDL. So I think for now, and given the time that we have today, it suffices to say once you've started something that has behavioral VHDL in it, just be a little bit extra aware of some of the gotchas associated with that. I don't think we'll be able to cover them all today. That could be a good use of a future session to talk about once you have that process block, or like your always block in Verilog. But once you have that process block in VHDL, you have to be a little bit careful of a few things that the textbook, the free range VHDL textbook mentions. Maybe it doesn't mention it in large enough font or something that it's not. It's there. It does say it. It maybe takes some experience with that. And then finally, I would add that it's extremely common for any design of any complexity that ultimately it's mixed. So you will see those keywords that describe your architecture, but those are just labels. You could have called it Joe or something, and that would have been a valid description. But we tend to use these terms of behavioral, structural, and data flow, as well as mixed, to describe um, what our intention was in the underlying implementation of an architecture in VHDL. And so for mix is just your design, excuse me, that has just some combination of things. It has some structures that we're port mapping together, as well as some data flow statements in there, because data flow statements are nice and quick and easy. It may have some data flow as well as a big process to do some behavioral stuff. It's not purely one or the other. And ultimately, when your design gets relatively complicated, you start to see more mixed mode designs in your VHDL. It's not just one or the other. Um, any questions about that? I can look through the chat here as well. So some concern that yep, I see that I said three styles. So three styles, and then you can mix them up. So whether that's a fourth or not, fair enough. Some concerns about your ability to draw effectively. I don't recommend freehand drawing like I'm doing it. So yes, if that's a problem, that's my problem as well. There are pretty good tools to allow you to basically, mentally capture your schematic. Visio is the Microsoft Office, official one that a lot of people do use. Um, just the name of it just changed. It used to be called Draw.io. Is one that I've used quite a bit. That's a relatively free and open version of that. That gets the job done. Our schematics this semester don't have to look any nicer than this. We should probably name the component something. Component A and component B. Name of the component, um, as well as uh, what the ports are on the component. You should label those. And oftentimes for your first few designs, we did the exact opposite in Lab 1, where we read a schematic and tried to figure out where that is in the VHDL, which I know was a little painful, but having your signals actually labeled is going to save you some grief in Lab number 2, and I'll try to create a video specifically on that point. So Draw.io is now diagrams.net. That one seems to work pretty well. I don't see any downsides of using that one. I don't recommend doing your drawing freehand if you don't feel like you're a good artist. The nice thing of having a digital drawing, of course, is our first iteration is never completely correct. So we need to modify things. We need to edit things. So a digital format makes life a little bit easier for that purpose. Another question we had is someone asked, for lab number 1, what style of VHDL were we using? Let's see if I can open up lab number 1 here. Everyone can see that that's in dark mode here. This is just the multiplier. I guess we could open up the quadratic or the Einstein. People don't all have that done yet, though. So for the multiplier, one hint would be that we use the word behavior here to imply that it's behavioral. But again, that is just a label. We could have called this architecture Joe, and VS Code is smart enough to let me know that's a problem. As long as I also, say that I've ended architecture Joe here, that's perfectly valid VHDL. May not be that useful to call something Joe versus to call something behavior, so we'll change that back. So this would be behavioral VHDL. And another instance where we would tend to see behavioral VHDL is, again, it allows us to describe sequential operations with those sequential signal assignments. It's very useful for synchronous circuits. So things that are operating relative to a clock, which is pretty common, but not every component we design would require that, is going to almost always be in behavioral VHDL. You could have done this design in Dataflow VHDL. There is a the when keyword in Dataflow VHDL would have allowed us to do this with one line of Dataflow. This is this is a pretty traditional way to design a brief synchronous circuit here. Um, there's something else I'd wanted to get to, but we can talk about, since I have this open, we can talk about this design. That's perfectly fine. So you have your process block. So that is the keyword that signifies that this is behavioral VHDL. Um, one gotcha that I think is pretty important here is that this goes back to, and I feel bad. We're not going to get to a couple of the last commandments here. You're gonna be under commanded here. But I would say one of the big gotchas here with this description is not the same as programming. Is there can be a thought process that can be very dangerous, where we actually are thinking of our circuit as being a function, and we have to be very careful not using that term, right? Our component is not a function, right? It is a very natural thing when we're writing code to have this type of structure, right? Where we have some function A that has maybe an input and return some output. And then after we do that, we take that result and we then call function B. That should be not f of A, that should be FA. So function A with some input, with some output that then goes to function B, and now finally some function that has function C, and perhaps the result of that function is what is our input to function FA. It's in some for loop or something like that. That is our program that we are writing in our C or Java or whatever sequential programming language we are using. That is, it looks at first glance very similar to what we are doing, but again, with our structural mapping, or our, even in this case, our behavioral description of something, it is fundamentally different. This is a module or a component named A, and it has some inputs and it has some outputs, but it's not a sequential relationship, right? It's MA that has some ports potentially that physically connect to this other part of our design B, that has some ports that physically connect to some other component in our design C. And it's not one, then the other, then the one after that. It is all three things existing concurrently in our design, and those wires are always active. There's always something on those individual wires. So the reason I say that is because when we look at this example of the multiplier, and it is behavioral VHDL, that first line of our behavioral VHDL looks a lot like a function prototype in C. Right? It kind of does, right? You can kind of squint your eyes and say, well, it's process, it's kind of like a procedure, and that looks like the three inputs to my function. And again, I'm not going to police the language we use with regards to describing our VHDL, certainly as you're learning, but that is definitely the wrong mindset here. Let's see if we can improve our font size here. Maybe I could just scroll up and it'll do it. Look at that. Beautiful. Okay. It does look like a function call in some sense, but it's not. What this is in behavioral VHDL is referred to as a sensitivity list. And you'll have some time to learn about this when you're forced to do the pre-labs each week. It does talk quite a bit about sensitivity lists, but that's what that is. This is saying I'm describing a piece of hardware, and those are the signals for which this piece of hardware is going to be reactive to, is sensitive to changes in those values. It's exactly the same as the always block in Verilog. And in fact, one common mistake that leads to a design that works perfectly well in Model Sim and it doesn't fail in synthesis, but it gives you the wrong result when you actually map it to hardware, is to have an incomplete sensitivity list. If I were to modify this code, and if the only change I were to make um, would be to remove this, in this case, it's a pretty simple design, would be to remove this clock from the sensitivity list, you would eventually maybe be able to get the entire design to work, but it's a fundamentally different piece of hardware because now it's no longer a synchronous piece of hardware. It's not really clear what this is inferring here. But behavioral is where you do run into those kind of traps, right? Where it does kind of look like a program that I'm writing, but we're using very prescribed ways of, in this case, inferring a flip flop in our design. We have a clock. There's a sort of built-in macro in VHDL referred to as rising edge of the clock. Once any of those inputs change, this circuit is responsive to that. It's responding to any change in any of those inputs. I know we have to go. We'll end things in just a minute here. If in any of those changes it's detected that we've had a rising edge of that clock has gone from 0 to 1, then the equivalent circuit here is what gets triggered. We have an output C, which is equal to IA multiplied by IB. And these are all integers. That's not good practice, but it's good enough for lab number 1 for this course. That is going to infer both a multiplier to do that multiplication, as well as an integer-sized flip-flop or an integer-sized register to store the result of what's happening on that rising edge of the clock. So we are still inferring hardware here. The risk becomes it kind of sort of looks like we're writing a sequential program here. They do sort of look alike at first glance, but this is not meant to be a C code analogy here. This is still a piece of hardware, a circuit with inputs that we care about when they change, and a very specific set of primitives that allow us to infer certain hardware functionality. For better or for worse, let's leave things here for today. I'll provide a very brief Lab 2 sort of intro video where I'll talk about rule number 3 and rule number 4. Rule number 3 is pretty important, but I don't have time to do it justice right now. In the meantime, as always, let me know if you have any questions. I'll stick around for a little bit today. And good luck finishing up lab number 1 and getting started next week on lab number 2. Thanks.